Hello, and welcome to my presentation on open source measurement technologies for electrical distribution networks. I am Dr. David Laverty from Queen's University Belfast in Northern Ireland. I have been working on measurement technologies for electrical distribution networks for 15 years, and I am the founder of the open source project OpenPMU. My work has applications in protection and control of small-scale distributed generation. In this presentation, I would like to explain why we need to measure the electricity distribution network and the rationale behind using open source tools. I will give you some of my perspectives on measurement technologies based on my experiences of installing and operating devices with industrial partners and through the development efforts in academic research. One of the first questions that comes to mind is, why do we need to measure the electricity distribution network? After all, the distribution network has operated for a century or more with very few measurements. At the low voltage end of the distribution network, down at the customer, typically the only measurement that is performed is energy metering, that is, how many kilowatt hours has the consumer used and how much are they going to be billed for. Typically, the electrical utility doesn't really have a need for a huge amount of information in the distribution network, definitely not at low voltages. But that's something that is beginning to change, and we'll look at why. But first, let's consider the topology of electricity distribution networks. The distribution network is essentially radial in design. Electrical power is supplied from a substation or a bulk supply point from the transmission system. The transmission system voltage is stepped down to a medium voltage. Finally, with the exception of industrial loads, that voltage will be stepped down to low voltage for supply to the consumer. Now, depending on where you live, the nature of the distribution network will vary. In North America, it's quite common for a few consumers to be connected to one transformer, meaning that the medium voltage network comes very close to their property. In European networks, it's common for a great many properties to be supplied from a single low voltage transformer. In fact, typically you would find up to 100 properties supplied from one transformer. The transformer, which steps down from the high voltage at transmission level to medium voltage in the distribution network, will typically have some instrumentation. This will give the utility knowledge of voltage magnitudes, currents, power flows. Typically, this data is communicated back to the control center via some form of SCADA network. This means that the utility gets updates on these attributes, perhaps every 10 seconds or so. This is useful in that it provides the utility with basic diagnostic information, helps with real-time operations, and the historical data aids in network planning. Of course, the challenge we face today is that we are demanding a lot more of our distribution network than we previously did. Today's distribution network is no longer a passive network. That is, it no longer simply transports electrical power from the transmission system to the consumer. No, indeed, the modern distribution network is highly complex. It's an active network now. And what we're aiming towards is to have a smart grid. It features renewable energy, for example, solar panels on people's roofs. It can include wind turbine generators. It has very high power loads, such as electric vehicles. And indeed, there is now an ever-increasing push towards electrification of things like home heating. This means that the distribution network now has to transport more power than it previously did, and it might also have to deal with reverse power flows. That is, power is actually being pushed from the distribution network back up into the transmission network. So, in order to understand this, the electrical utility needs much more in the way of instrumentation, so that they can measure more about what is happening in the distribution network, to understand the power flows, to understand the voltage profile, and to understand issues to do with power quality. There is a big drive towards having customer participation, that their devices will be able to interact with markets and trade, and at the same time, the grid must be reliable. Literature tells us that there's ways that smart grids can be self-optimizing, and indeed they must of course be cyber secure. The Phasor measurement unit is a device which is widely discussed in literature as having potential to enable observations within the smart grid. It is proposed for all sorts of operational real-time control and real-time protection schemes. However, industrial applications for PMUs are relatively limited. The reasons behind this vary on a case-by-case basis, but largely comes down to a matter of cost. That is, that the devices are quite expensive, they are expensive to install, and they have ongoing operational expenses, and oftentimes it is difficult to justify the business case, especially whenever the products are constantly in a state of flux and new features are appearing all the time. It's a classical case of why buy today whenever tomorrow's product is going to be even better. However, apart from the issue of cost, there is perhaps a more fundamental reason that care needs to be taken in terms of the enthusiasm for Phasor measurement units. The concept of Phasor measurement is indeed not new. It dates from the 19th century and has its roots with Charles Steinmetz. Phasor representation greatly simplifies the mathematical complexity when dealing with the analysis of complex networks involving sinusoidal voltages. Thus, they are perfect for analysis of electrical power systems. A phasor describes the amplitude and phase angle of a time-invariant waveform. That is to say, a phasor is only valid when the frequency of the AC power system is constant. This has very important ramifications for the use of phasor measurement units in real-time protection and control schemes. Let's consider briefly how the phasor measurement unit operates. The phasor measurement unit was described by Thorpe, Fadke and Karimi in the mid-1980s, and prototype devices were built by them. The basic operation of modern devices still relies on the same principles. That is that there are essentially three blocks. There is data acquisition, which converts analog voltage and current waveforms into numerical values. These numerical values are then applied to some form of signal processing, and from this signal processing we arrive at estimations of the magnitude of the waveforms, their phase angles, and other attributes such as frequency, rate of change of frequency, and whatnot. These estimated parameters are used to construct phasors representing the original analog voltage and current waveforms. The phasors are then tagged with the time at which they were observed, this time usually being derived from a GPS satellite receiver. The phasor and the time code are together known as a synchrophasor, that is, a time synchronized phasor. The synchrophasor is then communicated using an appropriate protocol, very often IEEE C37118.2. My interest in PMUs began in 2007 whenever I was considering using synchrophasors to address the problem of islanding of embedded generation. Whenever I started to investigate the PMUs that were available at the time, it quickly became apparent that the PMUs were complex to configure, they were unreliable due to various issues to do with hardware and software, and they were very expensive, particularly on a university research budget. Further investigation of the units that I had available revealed that they were based on very old IC architectures, meaning that there was realistically not much hope that a software update would fix the issues with them and major hardware revision would be required. It's worth noting that at this time, the IEEE standard C37118 did not yet consider dynamic test requirements for PMUs, that is, how the PMU would operate under, say, changing frequencies or rapid excursions in the phase angle. The application that I was concerned with really did only require communication of the phase angle of a secure point in the network to the embedded generators, where some logic would determine whether or not the distributed generator was islanded or not. Perhaps more important than the other aspects, at least from an academic viewpoint where this work needs to be published, is that the PMUs I had available to me were black boxes. That is to say that they were opaque in terms of their operation. A black box is a device which is described in terms of its inputs and its outputs, and the inner workings of it are not known. Vendors of this equipment treat their operation as a closely guarded secret, and they're very reluctant to share those secrets. Sometimes the outputs of these devices can be mysterious. That is to say that for the same set of inputs, or at least very similar sets of inputs, the outputs can be totally different. And that lack of consistency leads to problems, especially when doing research work. What I needed was a PMU which showed its inner workings, from the moment the analog signals are applied until the synchrophasor is transmitted. I needed a device where the full process that all the data goes through from beginning to end is fully understandable and fully transparent. That was my original motivation behind creating an open source instrument, OpenPMU. The fact that it ended up being a low-cost device was just a happy coincidence. It was not the original design goal. OpenPMU is inspired by the early work on phasor measurement units. There are 3 separate modules: measurement, phase estimation, and telecoms. These modules are designed to operate independently. They have well-described interfaces, which means that data can be pipelined through each module, but they are also highly swappable. That is, I can change the measurement module without affecting phase estimation and telecoms. I can change the phase estimation without changing measurement or telecoms, and so on. This has a lot of benefits because each one of these modules is a whole domain of subject-specific expertise. For example, the measurement module features analog to digital converters. These analog to digital converters must be synchronized to a GPS-derived clock so that we know exactly when each sampled value is acquired. Phase estimation, on the other hand, is more of a mathematical problem. It is a software optimization problem. It does not necessarily involve any skills related to hardware. And telecommunications is an area requiring detailed knowledge of protocols, standards, cybersecurity, and network theory. By keeping OpenPMU's modules separate, we allow experts on each particular area to focus their energies on creating the best possible solution for that task. In terms of the hardware required to realize an OpenPMU, there are 2 distinct attributes that are important. The first is that the measurement process is a hard real-time function. The analog to digital conversion process is disciplined by the time source. Again, this is usually derived from a GPS receiver. We know the time at which each sampled value of the voltage and current waveforms is acquired to within tens of nanoseconds. This metadata is passed along with the sampled values through the rest of the OpenPMU pipeline. The other important elements of the pipeline are the phase estimation stage and the telecom stage. The phase estimation stage is typically numerically intensive. It is doing transforms on the sampled value data in order to derive the phasor parameters, the amplitude, the frequency, the phase angle, the rate of change of frequency, and so on. The telecommunication stage is handling the network stack. TCP/IP, it is packaging and framing the data in whatever presentation format we're going to use, and it is dealing with cybersecurity aspects. Both the phase estimation stage and the telecommunication stage are not in any sense real time. They simply require a fast computer so that they can keep up with the pipeline of data coming from the hard real-time measurement process. In practice, using modern equipment, the fast computer in OpenPMU can be achieved using a Raspberry Pi. Virtually any other type of small embedded computer will also achieve this function. From a purist perspective, a phasor measurement unit only measures phasors. That is to say that the only data that a PMU should provide are synchrophasors. However, most commercial PMUs that are available are multifunction devices, and one of the most common functions you'll find on these multifunction devices, in addition to the PMU function, is that of a disturbance fault recorder. Now, that can easily be added in the OpenPMU environment by creating another module which sits and listens to the stream of sampled value data that comes from the measurement block. This module has functions which do transient detection, and in the case that they detect a transient, will save the sampled value data and indeed perhaps the synchrophasor data to local storage. It's very important to note that this is extra functionality above and beyond what a PMU is required to do, and the IEEE standard C37118.1 only describes PMU function, not any of the other functions within a multifunction device incorporating a PMU. Intermodule communication is achieved in OpenPMU using XML datagrams. The XML datagrams are streamed using UDP. The XML datagram from the measurement block contains the sampled values, and the XML datagram from the phase estimation block contains the phasors. Using multicast, it's possible for many modules to concurrently subscribe to the XML datagrams of each module. Pictured on this slide, the measurement block is realized on a BeagleBone Black, while the fast computer in our case is the Raspberry Pi. From this, you can determine that the bill of materials for an OpenPMU is really quite reasonable. Although XML is far from the most efficient way to pipeline this data, indeed, it does incur a processing overhead and it is byte inefficient in terms of data transmission, the benefits far outweigh the negatives. The principal benefit is that it is human readable. The metadata is all in plain text, and it's very easy to open a frame of data and see information such as the date and time at which it was taken, sampling rates, bit depths, number of channels, and indeed the names and types of the different channels. The sampled value data is encoded in base 64 so that the raw integer values are converted to ASCII characters, and these can easily be converted back into the integer values using tools in most popular programming environments. This means that people familiar with tools such as Python, MATLAB, LabVIEW can very quickly create applications using the OpenPMU system. Another great benefit is that the data does not have to be sourced from a hardware ADC. In fact, you can pipeline into the system data from simulation environments such as DIG Silent, or you can play back data that was previously recorded, or you can create arbitrary data using your own programs. The benefit of all of this is that you can prove the operation of a control scheme in simulation and be confident that whenever you put it into a real environment that it will behave in the same way. It will be operating the exact same algorithms, the exact same telecommunication systems as it would using real data from a real ADC as it does using the simulated data from the simulated ADC. Okay, so now that OpenPMU has provided a platform on which we can build open source tools, what are some of the challenges that need to be addressed? One of the first and foremost related to PMUs is what applications are they useful for? On this slide, we look at the goodness of fit of synchrophasors with respect to the sampled values from which those synchrophasors were produced. The sampled value data is plotted on these charts as solid lines, and the synchrophasors are expressed as dashed lines. Now, the synchrophasor tells us the amplitude, the frequency, and the phase angle of the waveform that was observed. It doesn't actually give us the raw time series data, but we can use the expression at the bottom of the slide to produce the time series data. Now, on the chart on the left, we see that the synchrophasors line up very well with the sampled value data from which they were produced. The system is essentially time invariant. However, on the chart on the right, there was a disturbance. There has been a transient event, which means that the raw sampled value data is not time invariant. It is in fact highly time variant. We see here that the disturbance is manifest in terms of a change in amplitude, a DC bias, and even a shift in the phase. The Phasor measurement unit has tried to produce a synchrophasor which expresses what is being observed, but it doesn't have the language available to it to describe what is going on. It can't describe a DC bias. It can't describe this unusual distortion in the waveform. So it is providing its best guess at a synchrophasor that roughly fits those. And we can see from the dashed lines that it's not a very good fit. Now, we can use tools such as goodness of fit to provide a scalar metric, which basically tells us if the synchrophasor is good or if it doesn't really match the sampled values very well. But how can we then use this in a real-time control situation? OpenPMU gives us the opportunity to explore in detail, are there ways that we can express what is happening better? Can we create new algorithms and put them into the pipeline? One of the surprising topics in the instrumentation community is that of frequency measurement. Despite AC power systems operating for over a century, frequency measurement is far from a solved topic. Many devices on the market estimate frequency in different ways, and whilst this is fine whenever the system is time invariant, whenever there is a transient event, the question is, which instrument is giving us a true reading, if such a thing is possible? The benefit of having an open source instrument is that no matter what measurement the device gives you, at least you can understand how that measurement was realized. You can look at the process by which the data was acquired, you can look at the algorithm that was applied, and you can decide, dependent on your particular situation, if that measurement is useful to you. Another such attribute is reactive power. Many instruments on the market claim to be able to measure reactive power, and the question is, what definition of reactive power are they using? So just like frequency measurement, having an open source device means that you can look at the whole process from where the AC waveforms were applied to where the calculated value of reactive power comes out and determine if this process is satisfactory for your needs and for your application. Likewise, there are many attributes concerned with power quality, such as harmonic content, flicker, and so on, which would benefit from an open source approach to their measurements. Now, for all of these things, frequency, reactive power, and power quality attributes, there are many algorithms, methodologies described in academic literature. Unfortunately, implementations of these tend to be somewhat limited, or they are done in a niche environment, such as perhaps a MATLAB script exists. The benefit of using an open source environment such as OpenPMU is that modules can be created. These modules then plug in and listen to the sampled values coming from the analog to digital converter, and they can have immediate use in practical situations. Modules in the OpenPMU system are written in the Python programming language, so the barrier to entry to create a mathematical function is very low. The biggest challenge facing open source instruments is that of certification to appropriate industry standards. Now, the measurement standards are usually relatively straightforward to achieve. That is to say that the literature points us towards methodologies that we're fairly confident will pass all the necessary measurement standards. However, the hardware must be certified against appropriate quality and safety standards. For example, many devices would require UL listing or CE marking in order to be qualified for use in given environments. These are expensive processes to go through and require essentially that the hardware becomes standardized and established, where the software can usually be changed without needing to go through a whole new verification process, although certain situations will require care and attention in that regard. The next big step in terms of open source measurements for distribution networks will be the creation of a hardware platform on which these software modules can be plugged in. This will transform the present state of the industry in which each function exists as its own discrete box that must be installed at great expense to the utility, to there will be a common platform. Much like how we install applications on PCs or mobile phones, we will have a measurement device where that measurement device is approved for use within the particular environment, and we can install onto that the particular measurement functions that we desire. The benefit, of course, of open source is that we have great confidence in how those measurement functions are being achieved. So thank you very much for listening to my presentation today. This has been a very quick overview of the drive towards open source measurement technologies for distribution networks. It really hasn't had the time to touch upon the application side where these open source measurements would be used, but essentially anywhere that you need measurements, you can use the open source measurements, and the key benefit is that by using an open source technology, you're no longer dealing with a mystery box, you're dealing with a device that you understand fully how the measurement process is achieved, from where analog values are applied to the instrument to where the data comes out of the instrument. So thank you very much. I'm delighted to be able to take questions either online now, or I'm happy to receive queries by email. Thank you very much.